Welcome to video number 4 in the Microfluidics course. Okay, so the topic of this video is microscale flow theory. Okay, so what I mean by that, what I'm going to be doing here is I'm actually going to derive our governing flow equations from scratch. And this is something that I think is really powerful, especially at the graduate level, for you to be able to see where these equations come from. And it even goes a little deeper than that. As engineers, we rely on calculus pretty heavily. And it's important to remember that Newton came up with calculus in order to describe things like mechanics, right? Fluid mechanics, heat transfer. And so when you see the equations like this derived, it helps to understand where these quantities come from, these dx's, these du's, and it informs your research you might want to do, because to get really deep into the theory, you have to know where these equations come from and you have to be able to derive them yourself. So we're first going to derive the governing equations for fluid mechanics, and then we're going to couple that with what we did in the last video where we looked at the dimensionless parameters. Okay, and we're going to use that analysis to derive the more simplified form of the equation that we actually use in microfluidics. So we're carrying forward what we learned in the last video. Okay, so let's get started here, and I'm going to write down these notes as I did before. So I'll talk over my note taking here, and I strongly encourage you to take your own notes, because that's been shown to be directly linked to how you retain the information that's being provided to you, right? So the more you do, the more consideration you have, the more likely you are to retain this. And also, don't just write what I'm writing, right? There's lots of things I'll say alongside it that help to describe what's going on here. So if you're making the decision to record some of these things as well in sort of the side margins, that even further enhances your ability to retain and understand this information that you're learning. Okay, got to make sure I turn on the recorder for my iPad here, so I'm not just writing and not recording it. Alrighty, so we have the Lagrangian description of flow and the Eulerian description of flow, right? And so Lagrangian, basically, we follow the fluid particles around as they flow. And Eulerian, right, we take sort of an overview of the bulk field of flow, right? And so we're looking at that space and we describe things that come and go rather than following the fluid particles themselves. But here's the thing, right? The laws of physics, they apply to mass. But the equations we have are Eulerian in nature, right? So we have a velocity field. So the description of flow is Eulerian. So what we want to understand is how we can relate the two, right? Because in fluids, the mass is moving around, right? So if the laws of physics apply to mass, we have to understand how we can write this in a way that we accommodate for the fact that the mass is moving. Okay, so we write our density field here. Meaning that density there is a function of position in space, the x, y, z coordinates, and t, which is time. We can write velocity like this as well. Velocity is a vector, so I'm going to put the bar on top. Okay, and then each one of these components here has that same kind of functionality. Right? Okay, so now we look at how we accommodate the fact that the mass is moving. So let's consider, I'll write this out here. Consider a fluid particle that moves a distance dx, dy, dz in time dt, and then the velocity changes by du. And from the chain rule, we can then write, okay, and what we're just doing there is because u can be a function of each of those variables, right? We're making sure we account for all of the changes that can happen. So the velocity can change in each of these ways, right? So just a quick note, right? So when we talk about dx, dy, and dz, we're saying it moves a distance dx, for example. What we're saying there is a differential distance, meaning just a very small distance that it moves. Okay, now I'm going to rearrange this so we can understand how to get du by dt. And this is a term that we're going to use as we move forward in our analysis for our force balances. Okay, so let me write this out here. I'll put P for a particle, right? We're considering a fluid particle that moves. Okay, and then I'm just rearranging this, right? So I've just taken the dt and divided everything out by this dt. Okay, now we may have already learned this, right? Depending how in-depth your fluid mechanics class was at the undergrad level, but this is the material derivative. Okay, and then what the material derivative is it's saying this is how we write acceleration in fluid mechanics, right? To account for the fact that this mass is moving, right? So we call this the acceleration of a particle, right? Okay, so we denote this as capital D U by capital DT, and it's called the material derivative. So I'll flip over to a new page now. Okay, so I'll write this out, and then we're going to talk about what each of these terms means. I can write U sub x there because I'm subbing in for the dx by dt term that we had from above, right? So we know dx by dt, position change in the x direction as a function of time, that's our velocity. That's our velocity component in the x direction. Okay, so let's walk through this now, right? So from left to right, we have du by dt, material derivative. So that's the total acceleration of a particle. And then the partial derivative, du by dt there, that's the local acceleration. So that's just if you have the particle sitting there and it speeds up or slows down, right? So u changes in time, that's our local acceleration. So then what is this other component here? So that's called the convective acceleration. Okay, and this is a change in velocity due to spatial position. Okay, so let me give just a quick example to make sure we understand this. So local acceleration, actually, it can be 0, right? If the flow is steady, for example. Okay, but we know actually even in a steady flow situation, we can still have a change in velocity, right? So this is what's covered by the convective acceleration. Let me just draw out a quick example. So if we had, say, like a little contraction like this, so the fluid is flowing from like a larger channel into a smaller channel here. So we'd expect the flow to look, you'd have the flow coming down here, right? From here, we go like this, and you get the basic idea, right? So essentially we know that particle here, let's say, I'll call that A. So because it's being forced into this more narrow channel, we know that it accelerates, right, to point B there. And that's a change in velocity due to our spatial position, right? So that would be accounted for by the convective acceleration component. Okay, so that's what that looks like. Now we're going to write out the material derivative in shorthand just for completeness. Just so we're familiar with the notation, we can write it as the u dot del u. So you recognize it when you see it. And then in the full form, because it's a vector, right? That's why I'm writing those bars over it to distinguish it. So we will do x. I'll write out x and y here. So we see all of the components. So how that would expand out like this. And that's I, right? Plus, I'll do it for y, and then we'll stop there. And I'll just assume you can piece together z, of course. And so I'll just write plus like dot, dot, dot. Okay, so there it is. There's our material derivative, all right? That's how we take care of the acceleration of a particle, total acceleration of a particle. All right, now get a new page here. Okay, so here we're going to derive the continuity equation. So this is conservation of mass. Okay, you might have seen this done before, but this, I think, is really helpful to understand where these equations come from, right? It helps us understand why and how we can use them, and we can derive them ourselves for more complicated situations, right? So we start with this elemental fluid volume, right? And so what that's defined as is a cube that has the dimensions right, of these very small differential coordinates. So it's dx by dy by dz, okay, as is drawn here. And now what we're doing here is we're looking at a very small point in space, right? So that's labeled as point O there, okay? So if we want to describe, right, the mass balance in this location, we break it out across this cube. So what we're going to have to do is we're going to have to use the Taylor series expansion, because what a Taylor series expansion does is says if we know, basically if we know the value of a function at one point, it can give us the function at other points. Okay, so I'll write that out here. And then I'll stop there. So we can keep adding, I'll put plus ... We can keep adding higher order terms if we want to, but we'll see that's not going to be necessary. So what we want to be able to do here is to do a mass balance of this cube. Okay, and to do that, we're going to need to look at all the mass that enters the cube, all the mass that leaves the cube, and the accumulation of mass within the cube itself, right? So we're going to look now at the right face and the left face. So the right face is right here. I'll color that in. I'll use like a green so maybe we can see that better. Okay, that's the right face. Left face, as I'll be calling it in this derivation, is over here on this side. Let me label that up as left. And to make the dimensions clear, so the right face has dimensions listed there. So it's dz by dy. And of course, the same thing over here. That's a dz. And that is a dy. Okay, let's get writing here. So what we want to know is the density at the right face. So we do that first. So what's the density at the right face? We're going to need this to do our mass balance, of course. So the density is, I'll use my Taylor series expansion. So I'll say if I have the density at point O, right, I need to add then the second term there, right? So that's f prime a. So di rho di x, right, at 0.0, because that's at a there. And now it says x minus a. So what that's saying is the distance you've traveled from point O, right? So point O is in the middle of our cube. So I'll give you just a quick second to make sure you're following along with me here, right? Like it's important that you're not just going through the motions, like actually try to be doing this yourself along with me. So our x minus a is actually going to be in the x direction, half the distance of the cube. So it traveled, so dx is the whole length of the cube. So we're going to write dx over 2, right? Do you see where that came from? Okay, then I have to do more. So if I need them, I'd have to do our next order term. I'll just show you what that would look like. So 1 over 2 factorial, and then it would be the x minus a squared now, right? So dx over 2 squared. But we are going to neglect the higher order terms, so I'll write that in a different color. Neglect higher order. Okay, and that's because we know from experience they do not matter. And this is due to the fact that in later grouping the terms, we'd find that they cancel off anyways. Okay, so let me just write this out then for our density and our velocity on the right face then, knowing that we don't need those higher order terms. So therefore, we're going to end up with the density expressed like this. I put those tails on the density because when I was writing notes for undergrads in the past, they complained that they couldn't tell the difference between P's and rho's in fluid mechanics. And so I put those tails on so it's obvious when I have densities, which is the rho, versus when I have pressures, which are the P's. Alrighty, left face, of course, you knew that was coming next, and hopefully you would just be able to write this out yourself now, knowing we follow the same procedure, right? It's just that instead of traveling, so x minus our a means the location that we're at minus the location we were at, right? So in the previous case, we moved positive dx over 2, but now the location we're at is to the left of point O, so we end up with negative dx over 2, so I'll write that out here, and then otherwise it's the same. Same thing happens in our x velocity, of course. So that's x velocity at point O. Also negative again. Alrighty, and now that we've taken care of left face and right face, I'm gonna need a new page for this, but we're gonna look at the mass flux coming in at the left and the mass flux out at the right. Okay, fresh page, mass flux in, right, coming from the left face. So that is going to be, so at the location of the left face then, the mass that is crossing that face is going to be the density at that location, right? Which is the mass over the volume. So the density there times the velocity that it's crossing that plane. So ux at that location multiplied by the area over which it's crossing, dA. Okay, and we'll double check with units, right? So we have density, kilograms per meters cubed, times meters per second, times meters squared, right? So the meters cubed on the top and bottom cancel. We end up with kilograms per second. Correct. That's what we would want for a mass flux. Go ahead and sub that all in from what we did previously. So our density at this location, written like this, just wrote this all out. So I'll just write it down here quickly. And then dA is, of course, as I have labeled up there, right? It's dy times dz. Mass flux out, okay, which is at our right face because we have positive velocity is in our positive x direction. So same basic idea, of course, density, velocity, area, and I will write it out again, trying to squeeze it in better this time so I don't have to write the area on a different line, but hopefully you're taking your own notes and you're writing this better than I am. All right, pulled it off. dy dz. Yes, excellent. Okay, now we got to do the net outflow. You could, of course, imagine that this was coming, and in spite of derivations being somewhat intimidating at the undergraduate level, it's actually not that bad, right? It's pretty straightforward. Okay, so what I end up with for the net outflow is I have to take the mass flux out, subtract the mass flux in from the left face, right, that we've just done here. So I will assume you know how to do the crankery through there of multiplying and simplifying, and you can probably see that we will end up with the following because of the terms that cancel and because of our simplification. Recognizing then rules of derivation, this is actually just can be written like this in our simplified form, reminding ourselves that point O is our point in space that we're concerned with. So to make sure in that point in space that we have a mass balance, this must be true, of course, considering all the flow in the x direction, right? Crossing those two faces. We'd have to do the same for all the other directions. So I'll write that out here. Of course, we don't need to see those done. You've seen the example in the x direction, so you know how it goes. So I'm just going to write the total net mass outflow here. I'll write it on a fresh line because I will not make it to the end if I don't. It's weird to write it on multiple lines. So it looks like this when we do all the sides of the cube multiplied by dx, dy, dz. Okay, so then we are balancing our mass, right? So that's the balancing of the total mass outflow here, right? So what that has to balance with is we say this has to equal the rate of change of mass inside the volume, right? The mass has to be conserved, right? Can't be created or destroyed. So So whatever crosses at the boundaries, of course, has to balance with whatever accumulates inside of this volume. Okay, let me flip to a new page here. Write this out. Make sure it's recording, of course. This must equal the rate of change of mass in the volume. And what, of course, how do we write the rate of change inside the volume? Again, I'll give you a quick second to think that through. So the rate of change of mass, right? So rate of change is a differential with respect to T, and our mass, in this case for mass, we're using density, right? As we do in fluid mechanics. So the net mass outflow is going to be the negative, right? So the change in density with respect to time. Density, of course, is mass over volume, so we do have to take into account the volume, and that gets our units to balance, right? So we had kilograms per meters cubed over seconds. Now multiplied by our meters cubed, we're back to kilograms per second. Always pays to do that quick unit balance there. So then I write out just what we derived just previously here on our last page. I'm definitely not going to have enough space, but let me give it a try here. And all of that is multiplied, I have to write it on the next line, but all of that is multiplied by dx, dy, dz. So hopefully you'll know what I mean there. And then it's pretty easy then to, I'll do this in a different color, just cancel off, of course, what's common to both sides and rewrite it on our next line here. So now we just have the following. Okay, and that's our mass balance. Awesome, right? Sure, you can just Google that and look it up, but now you know where it comes from. And I think that's super powerful. At least for me it was, as a grad student. Finally really understanding where these equations come from. And you can see we're just balancing the mass over like a tiny sort of small differential cube in space, right? And so now, of course, this equation says that whatever velocity field that is occurring has to follow this equation. This equation has to be true, right? And that's the restriction imposed by making sure the mass balances, right? So that helps us know what are real physical solutions of velocity fields and which aren't. So again, we'll do like we did before. So in compact form, just because this might help us to recognize it and also to work with it. The vectors there. Okay. We will write out our incompressible version of this because, of course, as engineers, that's a simplification we make all the time. What this means, I will remind you, is that we're saying the density doesn't change when we say something is incompressible. So the rate of change of density, of course, goes to 0, and density doesn't change in space or time. Both of them, right? So we just end up with this. And then for completeness, right? So the expanded form in Cartesian coordinates of our incompressible mass balance is the one we have very likely seen before, looking like this. Okay, awesome. Mass balance done. That's where the mass balance comes from. I'm going to need a new page and we're going to do our momentum balance. Make sure my screen is still recording here. Okay, so a momentum balance then, essentially exactly the same idea that we did for the mass balance, except in this case, it's forces. Conservation of momentum is actually the same exact thing as a force balance. And the relation between the two, as we remember, again, you might have seen this in undergrad, right? But the momentum is like density times the velocity. Okay, so we have, as if we have the rate of change of momentum in time is actually a force, right? And let's start by writing this out with Newton's second law. So you have force equals mass times acceleration. right? So if we had the momentum, it would be like mass times velocity, and the rate of change of momentum would then be mass times acceleration, right? So that's why we have this relationship between momentum and forces. So we think of this actually as a force balance. As engineers, I find it's easier to think that way. So we can express the total force acting on the fluid element per unit volume, right? We can write that based on what we've derived above. Okay, so the mass per unit volume, okay, is density, right? So I can write out density times acceleration. Now, what is acceleration? Of course, this is why we did all this work previously, right? So I can just now write down here, and hopefully you're ahead of me on this, right? What I'm going to write down, acceleration, right, of our particle is the material derivative, right? Velocity change over time. And we take care of convective and local acceleration, right? Because the laws of physics apply to mass. So this is the acceleration of total acceleration of a particle. And then this is going to equal something. And this something, that's what we want. Exclamation mark. Okay. So the total force then from Newton's second law is going to equal all the forces acting upon this fluid element here, right? So let's do that now. So let's start with looking again in the x direction, right? The right face and the left face. Now, I'm not going to do every single detailed step again, right? Because I did it once before. So I'm just going to skip ahead then. I'm going to say the surface force in the x direction, and I'll write this out just so you recognize what we've done here. Now, we remember, again, it might have been a little while since we've taken like a solids or fluids, so I'll just remind that what we're looking at is the stresses, right? So that's the force acting over an area. So when you see a normal stress, so the normal stress is written like this, I'll just circle one of them here, right? XX denotes the plane it's acting on, and then the direction that it's acting. So that first X and the second X. And then the shear stress, let me circle another one here. So this one's acting on the Z plane in the X direction. And that's a shear stress, so along the surface, whereas the normal stresses are, of course, normal to the surface. Okay, so this covers all the different kinds of things that can be happening to this sphere are covered by these shear stresses and normal stresses. So the surface force in the x direction, therefore, okay, I'm definitely not going to have enough space to write all of this, but you will get the basic idea here. So dFSX, differential surface force in the x direction. That's what that denotes. Let me try to write sort of small here. So we take the normal forces first, and we write out both the left face and the right face, and it's our Taylor series expansion, just like before, where we're half the distance from the center. Exactly the same idea, right? The area it's acting over, again, the same dy dz, and then because it occurs on both sides, right, we have the normal force on the other face, and I will squeeze in here like this is multiplied by dy dz as well. Leave yourself enough room there. I'd be writing this all day if I corrected every time I did that. Hopefully that's clear. Plus, okay, now we need, so these are all the forces in the x direction, right? So we've got to take into account, as I have labeled in that diagram I've included above there. So now we're taking, we just took like left face. I'm actually just going to erase what I circled from before and give you another color. Let's do that green. Okay, so we just took these normal faces, right? I've written them there in their Taylor series expanded form. Now we also in the x direction is all the stuff that's on the z plane, right? But is also acting in the x direction. So this is like the face that's facing us and the one facing away. And then we've got the y plane also has its x direction shear there and there, bottom and top. Okay, so we are going to account for all of these now, and because this has to be everything that's in the x direction, right? So I'll write those out here, and I think you get the basic idea by now where these all come from. and how, again, these derivations aren't too bad, right? We just need to balance everything. So there's all these forces, right, that act on this cube. So essentially just have to make sure I write them all out. And this I'm just writing from what's just above there in the figure, and then multiplied by the area that it acts over, dx dz. Same idea, again, squeezing this in here. Zx denoting like on the z plane in the x direction. So the change area in that case, dx dy. And if, I apologize, that might not be easy to read there, but that's coming from what's right above, right? So that one I just wrote is like, I'll box it up. That's from there, okay? And then multiplied by the area, so that's dx dy again there. Now I'll take a new fresh page here and make sure it's recording, of course, and then I will simplify all of that. Again, we have lots of cancellations, and we can write everything in a much more simplified form to look like this. Okay, now we have to take care of the body forces as well, right? So we can have the two kinds, right? The surface forces and the body forces. So we make sure we take care of body forces as well. So we say that's gravity, and don't worry because we're in our full vector form here. So just depends which way we're oriented in terms of which way the gravity is acting. But if we write it for completeness, we can write, so total force in the x direction then is all of our surface forces that we just came up with, plus all of our body forces, B for body, S for surface. And I will write that on the line below, learning from my mistakes here. So we'll just denote that as gx, right? Just in case we're oriented in a way gravity's in the x direction. And then everything else from our surface forces that we have was above there, all multiplied by dx, dy, dz, which I somehow still barely have enough space for. Okay, and then that denotes all the forces acting on the cube, right? So from Newton's second law, the total force acting on this element is mass times acceleration. So all of these forces we just described must equal to the mass times the acceleration, okay? And again, these are sort of our basic laws of physics, Newtonian mechanics, right? So I will write out now the differential momentum equation, which is as follows. So I'll do x direction first, right? The one that I just did. So then we write the mass, right, on a per volume basis times the acceleration, total acceleration there. And I'll use u as to denote the component in the x direction, u, v, and w. So I don't put the vector sign on that. Now I just write out what we just derived for the x direction. And this is complete, right? So we don't have to worry about simplifications yet. We're going to do that below because this is still a bit complex, right? When we have everything accounted for, there are going to be some simplifications that make this easier to look at. And this, of course, I only did the x direction in our derivation, but you would do the exact same thing for each of the other directions. There, all the normal stresses, all the shear stresses. Just while I'm writing this out here, a reminder that in fluid mechanics, which we will see in a second, the shear stresses come from the flow. So essentially that is the particles rubbing against one another if they have different velocities, right? And the normal stresses are caused by pressure. Okay, now we have a relationship for stress in terms of velocity, and this would take an extremely long time and be quite a divergence from our microscale flow equations, but there are ways we can relate the viscous forces and the strain. And for example, I do a complete analysis of that in the advanced fluid mechanics course, and there are places you can see that if you're interested in looking that up. So what we have here then is stress in terms of velocity. I'll just write that out so we get it in a complete form at least. Okay, I'll go to a fresh page to finish this off here. We do the normal stresses now. And we substitute all this in. We end up with the following. So it starts to look a little more familiar now. Okay, now we can do massive simplifications to this if we say that it's incompressible and it has a constant viscosity, so that's the Newtonian approximation there. We'll end up with the following. Just again, I'm only doing the x component here. So viscosity I can pull out because it doesn't change. We say constant viscosity, right? So now that leaves us with just this form, and now, okay, so now this is becoming familiar to you, and I'll just put like, you know, some dots here, and then some like dots here, so you remember that there are other coordinates, and then I'll just put in compact form, we would write it as follows. Vector form, so that's all of them, and we will definitely box this, of course. And that is our Navier-Stokes equation, the famous Navier-Stokes equation. And now you've seen where it comes from. So Navier was French. I believe he figured it out and published it in 1822. Stokes was Irish, who got it in 1842. He published that, and so we call that the Navier-Stokes equation. Now, that is our momentum balance with the approximations that we've listed there, the same one we described in our dimensional analysis lecture. So we can take this one step further, right? Let's do a non-dimensionalization on this, and then we'll simplify into the form we're going to use for microscale analysis. So this will be a complete analysis, so we've derived them all, and now let's see where we can take this with our simplification due to the dimensional analysis. So I'm going to need a new page for this. Okay, so here we go. So let's non-dimensionalize this. It's like a good practice of what we learned from before. What we do then is we choose our reference variables as we non-dimensionalize each of these. So we're going to say that U has some capital U. So reference velocity in the problem, we said before that could be like a free stream velocity. Our pressure, we're going to use mu times U over L. I'm just going to write a quick note up here. When we're at higher velocities, the way we scale pressure, it just simplifies the equation better. That's when we scale it to our dynamic pressure. But we use this following scaling that we have below for our Stokes flow when we non-dimensionalize it. So we're allowed to choose which groupings give us, like I talked about, that order 1 scaling, right? So we're really sort of trying to keep these terms sort of going from 0 to 1 in some sense, right? We want to keep these as order 1 terms. So the pressure in this case, we use this mu U over L grouping, and the U in this case is an average velocity, we say. And then my time, we can scale that as follows. So again, we know from dimensions that that will give us time. And I will just write the scaling for the del term as well, which is L del. And that's just a shortcut that I use there, right? So that's like a die by die something, right? It's an L multiplied in front of that, which we saw from the dimensional analysis how that worked also. So what that is, right? So di by di x prime, for example, would equal to L times di by di x. Substitution, right? To make sure it's dimensionless. Okay, so we need to go ahead and sub this all in. So we have our Navier-Stokes again. Let me write it here, and then we will simplify. So we've seen this done already, and I'm just gonna say we've already done this and scaled this, and we know that we can neglect gravity already because we've seen this previously, okay? When our gravity forces are relevant and when they're not relevant, okay? So we neglect gravity for Stokes flow, and we write this out remembering that this is the convective and local acceleration. So then if I simplify all this, I'll write it out here so we can see some of the simplifications here. Want to make sure and include enough steps so we can all follow where we're going with this as we get it into the, so all the primes there are the dimensionless versions of these variables. Okay, so that's all subbed in. Then we rearrange and we multiply everything through. So we're going to end up with the following here. Just go back and make sure all my vectors are in there and consistent. Good way to check and make sure the terms are all correct. Okay, so what have we got? We've got the Reynolds number right there, right? And we can see now, so we talked about what the terms are before. So I'll just kind of do a quick look at this, maybe with a different color here. So viscous terms we're remembering, so that was these ones over here, right? When we had our dimensions, that was viscous over there, pressure, of course, and then we have these are actually the inertial terms right there, okay? So Reynolds number, right, is a ratio of the inertial over the viscous. So we can look at now when the Reynolds number is very, very small, so much, much less than 1, we are dealing with systems that are either small, so let's say like a length scale less than 10 to the minus 3. We can have slow systems would also make this number small. So where our average velocity less than 10 to the minus 3, and we can also have very viscous systems, something also we looked at in our dimensional analysis where viscosity greater than 10 to the minus 3. Okay, and more than one of those can apply as well to have very, very low Reynolds numbers. And then so if the Reynolds numbers are very small, right, the Reynolds numbers multiply all these inertial terms out front here. So if we just get rid of those terms, then we end up with our Stokes flow. I'll put this actually on another page here. I'll go to a fresh page. So if Reynolds is really small, we completely get rid of that first term, and then we write the following like this, right? And put a nice box around that. So that is Stokes flow. And that usually we use that also with the continuity equation that we had from above. We mentioned, right, for incompressible. Okay, so usually we pair those two together when we're looking at microfluidic flows, for example. And this is a field called Stokes flow. Anytime we use this equation here, this form of the momentum balance. So in Stokes flow, we have negligible inertia, right? Very small Reynolds number. In Stokes flow, we have reversibility. It's easier for us to solve, so we actually can get exact solutions. We're going to look at that in an upcoming lecture. And we use this for microfluidics. So it's possible to get solutions for our velocity field when we use Stokes flow, coupled with the right geometry. So there we go. That's it for today's lecture. And just a quick summary before I close it out here. So what we did was we started by deriving from scratch our fluid mechanics equations, mass balance and the momentum balance. Essentially, so saying our mass would balance and saying that Newton's second law would apply for our forces there. Then we made some simplifications based on the dimensional analysis. We non-dimensionalized the Navier-Stokes and looked at a simplified form for small Reynolds number, and then we ended up with the Stokes flow equation there, and that's the equation we're going to use in microfluidics. So we've seen now where these equations come from, very powerful, learned how to derive things ourselves from scratch, so we'll close it out there. That's all for video number 4. Thanks for watching.